Hello friends, in this video lecture, we are going to discuss the single area steady state analysis. So let us begin. So friends, in the last lecture, we have discussed the block diagram representation for a single area load frequency control. Okay, this block diagram we have already discussed in the last lecture. So today, in this lecture, we will discuss the steady state analysis of this block diagram. If you see here in this block diagram, there are mainly two inputs we have. One is this commanded change in the output power, okay, and the second one is the change in the power demand. Okay, so these are the incremental inputs to the load frequency control system. Okay, this is the load frequency control system, and for this system we have these two incremental inputs. Okay, now initially what we will do, because we have these two inputs, first is commanded change in the output power and the second one is change in the load. Now initially what we will do, we will assume or we will keep this setting, that is commanded power output power, to be 0. How we can do that? We can do that uh, by keeping the speed changer setting fixed. Okay, this is achieved by keeping speed changer setting fixed. Speed changer fixed. Okay, and we will consider only that the demand on this system is going to change. Okay, now when the system is operating under such condition, when we have the fixed speed changer setting, then this mode of operation is called as free governor operation. This mode of operation is called as free governor operation. See, this question you might get in your vivas or orals. Okay, they may ask you to say, they may ask you this question. Explain what is free governor operation. Then your answer should be, when if we keep the speed changer setting as fixed, then that mode of operation is called as free governor operation or governor free operation. Okay, then as I said, let us consider that there is an incremental change in the load. Okay, suppose there is a incremental change in load is nothing but power demand. Okay, this would be our case 1, where we are going to consider only PD is changing, and definitely we will keep that speed changer setting as fixed, or let's say let us keep it to 0. Okay, now you see here, uh, I think you might have studied the control system. Okay, suppose if we have that simple control system, a simple closed loop control system, if we have, suppose this is gain A of this block, okay, and we are giving the feedback as B. Okay, this is input and let's say this is output. Then the gain of this control system, or the transfer function of this control system, is nothing but output by input, and we calculate it as 1 upon a upon 1 plus AB. We calculate the transfer function in this way. Okay, we need this basics of control system in order to uh, understand the response of this block diagram. Okay, so now here I'm considering that incremental change in the load by PD. Okay, suppose that load change is in step manner. Okay, earlier load change, incremental load change was 0. Okay, suddenly at a particular time it is increased by some step value, some finite value, it is changed now. Okay, now what is the, this will be the step signal, okay, in time domain. If I convert it to the Laplace domain, it would become 1 by s. Laplace of the step signal is 1 by s only. Okay, so whatever power demand, incremental power demand we are considering in time domain, if we consider it to be it into Laplace domain, it would become delta PD of S divided by S. It is because of the step change. Okay, now see, this would be the output change in the frequency delta F, and this will be the input. Okay, so now I want output by input for this block diagram. I need output by input for this block diagram. Okay, so just now I have discussed the things with you. Okay, what you have to do is we have to get this transfer function. Okay, let us try to get this transfer function delta f of s. Okay, of course, uh, this is output and input would be delta pd of s upon s. This is the input. Of course, we are finding this at keeping speed changer setting fixed. Okay, so we'll get here. One more thing I want to add here. You see, this incremental input is having a negative sign here. It is having a negative sign here. So of course we should write here a minus sign. Okay, because it is a negative signal. Of course, again here, if you see in this block diagram, as it is zero, as we are keeping it to be zero, so this summing block will go, and we can have a direct connection here. Okay, because this signal is zero here. Okay, so even though we have that summer here, but physically it will not have any importance here. Okay, it will not have any impact here. Okay, so with that, you see, first we have to write the transfer function of a block A, or the gain of the block A. Then we have to write it in terms of a 1 plus AB. Okay, so the block A would be kps divided by 1 plus stps. Okay, so let me write that kps upon 1 plus stps, whole thing divided by 1 plus, you see, we have to take the gain of all the blocks in multiplication now, because all these blocks are connected in series. 1 by r, this block into this block. Okay, so we'll write that. I'll keep that 1 by r later. First I'll write ksg speed governor 1 plus s tsg will get here. Okay, into kt turbine gain 1 plus stt turbine time constant. Okay, into 1 upon r. Okay, so we get this. Now what we can do here is, let us multiply and divide with 1 plus s tps, because I want to cancel this. Okay, as we are multiplying in the numerator, then of course we should multiply it in denominator as well, so as to balance the equation. So s tps. Okay, now let us write it in simplified way. So I'll shift this denominator on that side now. Okay, so here I'll get change in frequency, that is del fs. Okay, at speed changer setting fixed, it is equal to, now it is negative now, so I'll write that minus sign first. Okay, now what is happening here, that 1 plus stps 1 plus stps will get cancelled. Okay, now in denominator, you see, when I multiply this in the bracket, it will get multiplied here with 1. Okay, of course, I think we have not written here the gain of that main block as well. Okay, we should write that should also come kps, because it was 1 plus ab, so a should also come 1 plus stps. Okay, now we are multiplying it with 1 plus stps as well. Okay, now when I multiply this 1 plus stps inside, so definitely it will get multiplied with this one here, but in this case it will cancel out this. Okay, it will cancel this. So you just see what we will get here. In the numerator, of course, we're left with kps, because denominator is gone now. Okay, and in the denominator we will have now this bracket will get multiplied with the 1 here. So we'll get here 1 plus s TPS. Okay, then this terms 1 plus that KSG KT KPS KSG into KT into KPS upon R. I'm writing this way, divided by these two time constants or these two terms, 1 plus S TSG and 1 plus S TT. Okay, and of course we are shifting that term on that side, so we'll get here delta PD of S upon S. Okay, now I want to get the steady state value for this. Okay, I need a steady state response of this delta F, that is change in frequency. Okay, when how we can get that? You should have a knowledge of control system to understand this. Okay, that steady state value we get. So let me write here F. See, particularly I'm writing it with small f because it will represent a steady state value. Okay, the change in frequency, steady state value of change in frequency, of course it should be at keeping this settings constant. Okay, or keeping this settings fixed, it should be 0. Okay, so this would give us steady state value. It is steady state. Okay, when we will get the steady state value, for that we need to apply the limits. Okay, so limits s tends to 0, s into del f of s. Okay, this will give us the steady state value. Okay, how to get the steady state value? You have to apply the limit over s tends to 0, s into del f of s. Okay, that we have to find. Of course, this del f of s is nothing but it is at this value. Speed changer setting is fixed. Okay, now let us try to get the steady state value for this function. Okay, so that del f, of course, at del pc is equal to 0, it will give me now see this limit s tends to 0, s into this whole term. Okay, s into this whole term we have to write. So negative sign we have, so I'll shift this negative sign on the here. Okay, then we get kps into del pd of s, whole thing divided by, see here we get 1 plus s tp of s plus that ksg into kt into kps upon r. We have in the denominator we have 1 plus stsg into 1 plus stt. Okay, so again upon s we have. Okay, so here you see this s and this s will get cancelled. So let us apply the limit. Okay, when we are applying the limit where it is saying s tends to 0, so the terms where s is having, it will become 0. So this bracket value it will become 1, this bracket value it will become 1, and this bracket value it will become 1. So we get here, we are getting a value here as the steady state value we are getting here as minus, it is kps. Okay, minus kps divided by these terms we are getting 1 plus ksg into kt into kps upon r into delta pd. Okay, so this is the steady state value of the change in frequency. Okay, now you see here this kps, ksg, kt, these are the gain. Okay, these are the gains of the various responses or the various blocks in that block diagram. Okay, So now here you see that KT, it is a gain of the turbine and it is a fixed value. Okay, it is having some fixed value. Okay, then that KPS, it is a gain of the power system. Again, it is also fixed. Okay, it is also fixed. Now we left with only one gain, that is KSG. That is the gain of the speed governor. Now this KSG is adjustable. KSG is not fixed, it is adjustable. Why? Because it is adjustable. We can adjust the value of KSG by adjusting the length of those linkages. Okay, if you recall that diagram where we have seen that speed governor system, there we have seen that mechanism which is having the linkage mechanism A, B, C, D, E. Okay, if we change those lengths L1, L2, L3, L4, then we can change the value of this KSG. Okay, so practically in power system, what is done? This KSG is so adjusted that this product of KSG and KT will be approximately equal to 1. Okay, it is done by adjusting the KSG. Okay, it is so adjusted that this product is approximately equal to 1. Again, now this KPS, as I am saying, it is a fixed value, but of course that KPS is having some uh, value, it is equal to 1 upon B, and that B we have already discussed. It is a power system constant. Okay, we can call it as a damping constant as well. Okay, that B is nothing but B we have discussed. It is dou PD upon dou F. Okay, for change in power demand, what is the change in frequency? Okay, that is nothing but the constant B. Okay, if I divide it with the PR, that is the kW rating of the alternator, then it will give me the per unit value of this B. Okay, and this B is having a rating as megawatt per unit change in frequency. Okay, of course it should be in per unit because we are dividing it with PR. Okay, now with this, this term, it is del F. So this term will become now del F is becoming now KPS. Let us put it equal to 1 upon B divided by this KSG KT is becoming 1. Okay, so we'll get here 1 plus 1 into that KPS is nothing but 1 upon B. Okay, so we'll get here 1 upon BR. Okay, uh, again it is multiplied with change in power demand. Okay, now let us rearrange this. Of course we have the minus sign here. Okay, when you rearrange this, you should get del F as, okay, if I shift this B down, so I will get 1 divided by that B will get multiplied here, B plus 1 upon R into change in power demand. Okay, or change in the demand. Okay, now you see here, for this change in the demand, this will be the change in the frequency. Okay, is it something related to, if you remember your geometry or basic maths, you see we have this equation y is equal to mx plus c. This is the equation of the line. Okay, let us suppose that constant is not there. Y is equal to mx. So this is the equation of the straight line where m is the slope of the line. So I can relate this equation with this equation where this is the output, this is the input, and this will be the slope of the line. Okay, now with this relationship, we'll draw the plot of frequency versus the power demand. Okay, frequency will take the frequency in percent and we'll take the power demand in percent. Okay, power demand or load in percent, and we'll see how we'll get that plot of these two. Okay, I have that plot with me. Let me just copy and paste it here. We have this plot of, you see here, it is this y-axis, it is representing frequency in percent, and this x-axis is giving percent load. Okay, you see we have got this response when the speed changer setting was fixed. Okay, now uh, for frequency, for 100% load we are getting a frequency 105. See, practically we cannot go beyond the variation in the frequency, or we cannot go more than 5% of the scheduled frequency. Okay, we have to maintain the frequency within some band. Okay, and practically we should not go beyond 5%. Okay, uh, even though these days we are operating frequency at plus or minus 0.5%, but practically we have to take care that it should not go beyond plus or minus 5%. Okay, so that is why with this relationship, if I plot the graph, or I'll get this type of the droop here. Okay, this is a droop. Okay, which is having a slope equal to minus 1 divided by b plus 1 by r. Okay, uh, see, for 100% load with speed changer setting fixed for scheduled frequency, we are getting frequency as 105. Okay, now if I reduce the load, okay, of course, when you are going to reduce the load, the speed should change and the frequency will also change. So here with speed changer fixed, we are observing here that the frequency is reducing. Okay, earlier it was the 105. Okay, now it is 103. Okay, so this is representing the droop. Okay, droop of the frequency and the load. Okay, now practically this slope of this droop, or this the constant b in the power system is having a very negligible value. Okay, typically if we consider a system for a particular system, we get this value of b as 0.01 per unit. Okay, and megawatt for unit change in frequency. Okay, whereas the value of r for a typical power system, it is 1 by 3. Okay, so if we consider these values, we can say that as r is very large as compared to the b, we can neglect the b. Okay, when we neglect the b, the slope of this line or this equation, it will become, when we neglect the b, so this frequency change in frequency will become, see, this b will go 0, 1 divided by 1 by r. So r is in denominator's denominator, it will go in the numerator. So we get here minus r change in load. Okay, or change in the demand. So we can say that, I should write here approximately. So we can say that this droop is mainly contributed by this R. And what is this R? It is the speed regulation of the speed governor system. Okay. So now this R, it is naturally so adjusted that it will not let the frequency to go beyond this range. Okay, that is plus or minus 5%. Okay, this R typically or practically it is so adjusted that it will not let the frequency to go beyond plus or minus 5% for the change in the power demand. Okay, so this is what we get when we get the uh, speed changer setting as fixed. Okay, we can see here, as the load is changing, the frequency is changing. Okay, but because of this r, the change in the frequency is not much high. Okay, the change is very small here because of this r. Okay, one more thing we can uh, understand from this group characteristics is that when load is increases, when the load increases, it can be compensated in the power system in two ways. Okay, let me show you here. If the load is increases, if you want to compensate this increase in the load, compensating means you have to supply that load. Okay, it can be done in two ways. One and second. The first one is the generation increasing. Okay, we can increase the generation to meet the increased load, or second thing is we can reduce the load. Okay, we can reduce the load. Practically, in practical power system, 97% we go with increasing the generation. Okay, 97 plus. Okay, specifically let us keep it as 97%. 97%, the increase in the load will be compensated by the increase in the generation, and only 3% compensation is done by reducing the load. Okay, so this we can understand from this group. Okay, again, let us go for the case 2. Let us take the case 2. Now in case 2, what we will do is that incremental uh, power demand will keep that 0, will keep that PD as 0, and will now give the commanded change in output. Okay, okay, we will give this command now. Okay, let us see how this block diagram will respond to this. Okay, so now you can see here in this case the input will be, this will be the input. Okay, and the output will be change in the frequency, this would be the output. Okay, now of course I want output by input, that is the transfer function of this block diagram. Output by input I'm looking for, and that to at this PD of S is equal to 0 at this time I'm looking for. Okay, now you see that block diagram. Now just refer this block diagram. This is the input now, and this is the output. So these three blocks will be acting as A, and only this R is acting as B. Okay, so A divided by 1 plus AB we have to write. Okay, to get the transfer function. So we'll write here this way: A divided by 1 plus AB. So that A, it is having gain as KSG, that is the first block, divided by 1 plus STSG. Okay, second block KT divided by 1 plus STT into KPS divided by 1 plus STPS, that is the A block, divided by 1 plus, this whole blocks will come again and will get divided by, or will get multiplied with that R. Okay, KSG divided by 1 plus STSG into that KT divided by 1 plus STT into KPS divided by 1 plus STPS divided by R, or multiplied with 1 upon R. Okay, we'll do the same thing here. Now we will multiply and divide with all these three brackets, because I want to cancel all these three brackets. If I multiply and divide with all these three brackets, definitely in the numerator all these three brackets will go, and of course in this term also this will go, but these brackets will get multiplied with this one over here. So we will get an equation here as, see, we'll get this equation as delta f of s, okay, at demand as constant. Okay, we get SG, KT, KPS divided by all these three terms will come. 1 plus S TSG, it is TSG, into 1 plus S TT into 1 plus S TPS. Okay, plus these terms will come now. Okay, so these terms are KSG, KT into Kp of S divided by R we get here. Okay, again I want to know, or I want to get the steady state value of this. Okay, of course we should have that output here, that is delta Pc of S command, and it should be get divided with S. Okay, I think I have not written that S here. It should be get divided with S, because again we're giving the command to change the output power in step value. Okay, we'll give certain definite command so that the output will change with some certain step value. So again, step signal is coming means Laplace of step is 1 upon S. Okay, so we get here, I want to get the steady state value here. So steady state value at delta PD is equal to 0 would be, you see, we have to apply this limit s tends to 0 s into del f of s. Okay, that will give me the steady state value. Okay, so let me write directly value we'll get here, because when we multiply with this s and that s will get cancelled, and all these three brackets will become 1. Okay, 1 into 1 into 1, it will become 1 only. So we get here del f specifically at PD is equal to 0, we'll get ksg kt kp divided by 1 plus ksg kt kp divided by r, of course, into that del pc, because that s will get cancelled. Again, you see here, we do the same thing. Ksg, let us adjust the ksg such that ksg into kt approximately equal to 1. And again, we do have kp is equal to 1 upon b. Okay, so if you put these things here, if you put up these things here, okay, so you will get change in frequency as, again, it will be, now this time we don't have minus sign. Okay, we are having the plus sign only, so it will be 1 upon b plus 1 upon r into that speed changer setting. Okay, del ps is nothing but the speed changer setting. Okay, so this is what relationship we are getting when we are keeping load or the incremental load to be 0, and when we are speed changer setting is varying. How this frequency will vary, we can understand with the help of this law. Again, we have discussed when the speed changer setting is fixed and when the load is varying, how the frequency will change. Okay, now let us combine both the effects. Okay, let us suppose that now there is an incremental change in the load, as well as there is an incremental command to change the power, or there is an incremental command to the speed changer setting. So in that case, we can get the uh, a resultant change in frequency with the help of superposition theorem, because you see, their slope is same. So we'll write here 1 divided by that b plus 1 upon r into, we get here del pc minus del pt. Okay, that is very important equation here. Now what we can conclude from this equation? Okay, the conclusion is very important here. You see, when, suppose, this delta PD power demand is changes now. It got changed. Either it will be a positive change or a negative change. Suppose load is increasing, then of course this will have a positive value. Okay. As and when the load is changing, suppose correspondingly, if I give the command to the my speed changer setting. Okay, if I change the speed changer setting in such a way that this del PD is equal to del PC, then in that case you can see that change in frequency comes to be 0. The change in frequency, it becomes 0. Okay, so now let us get back to that plot. Let us get back to that graph. Okay, in this case, speed changer setting was fixed. So that is why as load was changing, there was a change in the frequency because of this trope. Okay, now if I keep the, or if I don't keep the speed changer fixed, if I allow it to vary in proportion to the change in the load, then in that case, when the load was 100%, of course we'll get the scheduled frequency. Okay, of course we'll get the scheduled frequency. Okay, again, suppose if the load is changed now from 100%, if it comes to 60%, if we give the proportional change in the uh, command to the speed changer setting, then in that case we may get this graph. Okay, where the frequency will remain same for any load. Okay, so this is how you can get the steady state response of a load frequency control for a single area. Okay, in next lecture we will discuss the transient response of this block diagram. Okay, Thank you very much.